Okay, so the last thing we should talk about is the Ote Solvers in Matlab, which there are a bunch of, and they're pretty cool. You might have seen these before in other classes, but it's the same idea as in ease in that it's up to you to program your state equation. You have to make that some kind of a function, and that function needs to take in time and temperature and return d-temperature, d-time. And once you've built that function, then it's just a matter of calling one of the ODE solvers to integrate through time. So here I built a function. Let's see if I can find it. D-temperature, d-time. So I called it d-temperature, d-time lecture 14. I guess I'm off by one. It takes in time and temperature. It does whatever it needs to do inside of here to calculate d-temperature, d-time. So this is up to me. Right? I wrote all of this, and I should probably make sure it works right and everything like that. But once it's done, then you just basically tell the ODE solvers where that function is, and it will call that function as it needs to move through time. So this is how those work. We're going to do it for ODE 45, but there's a bunch of them, and they all have pretty similar calling protocol. You call it ODE 45. The first argument is the name of the function, or at least a mapping to the function, which we'll talk about here in a second. The second is the span of times that you want to integrate from. So if I just give it 2 times, like I give it a vector that has 0 and t, sorry, this is hard, t sim, it's going to integrate through these times and then give me back information about every single time step that it used for that information. If I only want information at a certain set of time steps, then I can actually give it here a vector of those times, and it will give me them back only the temperature of those times. It, again, will have nothing to do with the time steps that are actually used in the integration. This is just a way of controlling the output. So it's like in the integral table, when I gave time a certain step, it would then only give me back the information at those times, but it had nothing to do with the actual integration. Okay, and then the last thing here is the initial value of the temperature. So over here I get back a vector of times, and at every one of those times a vector of temperatures. And again, if this is a vector here, then this vector here is exactly the same, because it's going to use the same times to give me back the vector of temperatures. Okay, so let's see what this looks like. I have hopefully somewhere, so right here, a call to the ODE 45. So here's t initial. I'm going to simulate 0.4 seconds. My first argument is the name of that function. So this is the function I wrote. I'm going to get every single time back, and I'm going to start at 300 Kelvin. And this should just work. If I run it, you can see this is temperature as a function of time. Okay, so again, a few things that we should talk about to make this more useful. One thing is that the way d-temperature, d-time is set up right now, you'll see that I had to put all these inputs into the function itself, which is not very convenient if I want to run some kind of a study where I change the diameter of the sensor or the heat transfer coefficient or something like that. Because these aren't inputs, it's hard to vary these, right? So I'd really rather have a state equation function that looks like this, where yeah, I give it time and temperature, but I also give it other inputs that I'm interested in varying, right? If I do that, then I can't call ODE 45 the way that I called it previously, right? So here's ODE 45. Let me get rid of some of these. This is me calling it with this new dt time, right, that has additional inputs. If I try that, it's not going to work. It wants a function here, this first argument, it wants a function only of time and temperature. So it's not going to know what to do with this function that has more inputs than that, right? So what I have to do is I actually have to map this function call here onto a function of only time and temperature, right? And you do that with the mapping in Matlab. So let's do that. So here's ODE 45. Here's the function call that I want to use, but I want to map that onto a function call only of time and temperature right here, right? So this mapping will allow you to do this, right? You'll notice here I've set all these inputs and they're passed into here as well. So if I run this, it should work, I hope. Yeah, so there it's running, and I can look at the solution. So that's one thing that's useful to know about, is this mapping. The other thing that's useful to know about is you can add a fourth argument, options, which just basically controls the numerical integration process, right? So options is a vector that has every one of the settings that you can use for that integration process specified, right? And the way that you adjust that is with this thing called ODE set. So if I just set options equal to ODE set and don't have any arguments here, then I'm going to get the default settings, right? So here I'm getting a vector now. The vector is basically the default that you would use. Let me put this back to ODE 45, and I put it here as a fourth argument, and I should get not basically, but exactly the same answer that I got before, right? But if I look at how ODE set works, if I type in help ODE set, you'll see that this thing consists of a whole bunch of different things that I can control, right? So the obvious ones are the tolerances, so the relative and the absolute tolerances. There's a whole bunch of other things that I'm not sure I know all of what they do, but you can control them if you want. If you don't do anything, then rel-tol is set to 1e minus 3, so 0.1%, right? So I just ran it at 0.1%. The absolute tolerance is set to 1e minus 6, so I just ran it with that. If you want to change these things, and the way you do that is also with ODE set. So you give it both the parameter you want to change and then the new parameter, right? So I ran this with 1e minus 3. If I want to change that to 1e minus 8, I would call it rel-tol 1e minus 8. And I can keep putting in pairs of parameter, name, and value, as many as I want inside of here. Right? So if I run this now, I should see that because I have a smaller tolerance, I need many more time steps. Right? So did I run it? Let's run it and look at it. And you should see that there's many more time steps, and you can see the variation in the time steps here as well. So that's how you control the integration process. Yeah, okay, so that's pretty much everything about lump capacitance, analytical and numerical solutions. You sort of by accident learned a whole bunch about how to do these numerical integrations, which I think is super useful. In a few lectures, we're going to come back to these because we're going to be doing transient conduction problems where we can't ignore temperature gradients inside the material. And so instead of just having one temperature that represents the entire material, we're obviously going to have a whole bunch of temperatures at a whole bunch of nodes inside of the material. So instead of having just, in this case, one state equation that I'm integrating through time, we're going to end up having a bunch of these that we integrate together through time. So all the same integration techniques, we're just going to have a set of them instead of just one of them.